Hello and welcome to this year's summer school here at your Dortmund University. My name is Sebastian Buschjäger and I'm going to talk about fast inference applying large models on small devices. And before we dive real deep into the topic, let's give a quick introduction why inference really matters or why this topic is so interesting. And I think most of you will know that self-driving cars are somewhat in reach at the moment. So we do have the first beta versions basically of software available for a self-driving car. And for example, Tesla uses deep learning methods for image recognition and steering at the same time. So their deep learning model must be applied continuously on the quote-unquote small device, which is a car in this case. And well, Tesla uses electric cars, so it's a natural question to ask how much energy does this feature consume? And as you might know, deep learning is very energy hungry or resource hungry. So the guys from Tesla decided, okay, let's use our own chip. This is more efficient. And it is said that this chip roughly requires 75 watts of energy to run. So I was wondering, how much energy does that mean if we apply this feature on a large scale, let's say in Germany, in all the cars? So in Germany, it is estimated that the combined number of kilometers traveled by personal cars in 2018 is roughly 630 billion kilometers. That's a huge number. And now if we take the average speed of a personal car in Germany, we can roughly calculate the hours this model has been applied or should be applied in the case we would use it in all the cars. And this way we could calculate the total energy required. And I would just ask you at this point what your guess would be, how fast cars on average travel here in Germany. And we will discuss that later during the Q&A session, what you came up with numbers. The one I used here led to the conclusion that the autopilot would require roughly 0.79 terawatt hours of energy. And first of all, that's the number for me. I have no idea what that actually means. This is so far off the scale from what I'm used on a daily basis that I need to look it up, what that number means. And as it turns out, the largest run-of-the-river hydroelectricity plant in Germany roughly produces 0.79 terawatt hours. So differently put, we need one electricity plant to produce the amount of energy required if you would use the autopilot feature in all the cars in Germany for 1 year. And I think that makes it clear that we need to watch out for methods which are more resource efficient, so we don't need to build new electricity plants for something like this feature. As a second example, let's look at search engines. These are still the main entry point to the internet. And believe it or not, Bing.com is the second largest search engine behind Google, because Bing.com also powers Yahoo, Amazon, Alexa, and all that stuff in the back end. And what's cool about Bing.com is they use a ranking algorithm to rank your search results. And specifically, they use gradient boosted trees. And now you might say, well, trees are easy. They don't require much energy, do they? And so I don't know how fast the pipeline from Bing.com actually is, but we can just assume that, let's say, it requires 1 millisecond to rank a single query. So in other words, 1 millisecond to apply the model once for one search query. Then we can do the same calculation we just did for the Tesla's autopilot. And so we can find these numbers online. So there are basically 12 billion search queries per month worldwide to Bing.com. That means roughly 4.5 million queries per second worldwide. Now, assuming we run that on a desktop CPU, so for example, an Intel i7, which uses approximately 91 watts, we would require roughly 4,500 CPUs to keep up with the number of queries. Again, calculating that over the year gives us 3.57 terawatt hours. So this is roughly 4 to 5 times more than the autopilot feature already uses from Tesla. And again, for reference, I looked this up. The largest black coal plant in Germany produces 3.43 terawatt hours in a year. So an entire coal plant is required to run the ranking in Bing.com. Of course, this is a kind of an unfair comparison here. This is just a very rough computation. We didn't talk about how how much energy a browser uses, how much a query actually uses network-wise. So there are routers involved, there are different parts of the server involved. There's a lot of processing going on behind the scenes. But if we just look at the machine learning model, we still come up with 3.57 terawatt hours. And I think that's a lot. So in order to tackle this problem, we need some basics. And let me quickly recap what you hopefully know about machine learning so far. So usually we would formalize a problem mathematically, then we can design an algorithm to solve this problem and in the end implement a solution. Now, some problems are very difficult to formalize exactly. So if you look at these 5 pictures, we see 4 pictures with a dog and 1 picture with a cat. And now the question would be, what is the mathematical representation of a cat? So the idea in machine learning is, okay, we will not formalize a problem formally, but by label examples. And that's what we would call the data. Then we have a set of targets, for example, in a binary classification setting, -1 or +1, which could also be dog or cat, or in a regression case, maybe all the real numbers. Of course, we have the labeled data. X is the input. This could be an image. This could be a feature vector, whatever. And Y, that's the label. Then we look at a set of models. So this is a set of functions mapping from the input space to the output space. So given an X, we can assign a label to that. And for example, this could be a linear function in the case of a simple linear regression. Then we often use a loss function, which takes 2 different labels and maps a loss onto those. So for example, if we take the true label and compare it to the one predicted by our model, we want to quantify how good or how wrong that is. And we use a loss function to do so. And now machine learning in a nutshell would basically mean that we, given this set of functions and given the data, we would like to find the best fitting model given the loss function. So the empirical loss should be minimized given the data we have. And the resulting model F star, this is what we are going to talk about in this talk. So we kind of assume, okay, this model F star should be run on a resource-constraint device in the end. And so we need to think about how this model F star actually looks and how we can apply that efficiently. We're talking about 2 different kinds of models here. The first one will be neural networks. And I will not talk about specific architectures or any specific types of neural networks, but more about the regular feed-forward / maybe convolutional neural networks, but nothing more fancy. The other one would be ensembles of decision trees. That's a well-known method. It still performs very, very good. In many applications, it's the go-to method to use. So this is kind of a second example we are using. Now let's quickly recap how the CPU works and what memory hierarchy is. So there is something which we would call the memory wall. So CPUs have become much, much faster than memory. And so in order to cope with that, the CPU designers came up with different levels of different memory. So cache would be a very small but quick memory, so the CPU can access this very, very efficiently and fast. If we have multiple CPUs, we usually have a shared cache, which is slightly bigger than cache 1 and cache 2 in this setting, but also slightly slower. And then from the shared cache, we could access the main memory, which is even bigger, but even slower. And then on the next level, there would be, let's say, the disk or the solid state drive, whatever. And this would be even bigger, but even slower. And by this, by putting stuff in the cache, we could hide this latency and the access speed the main memory, for example, has. And we would mimic a fast system. So let's look into the CPU first. What's the instruction set architecture of a CPU? So basically, we have pipeline processing. I depicted here a pipeline with 4 different stages. So the fetch unit or the fetching stage would get the next instruction. In a decode stage, we would decode the instruction to see what it actually does. And then in the next stage, the execution units would assign the proper instructions to be executed, for example, a multiplication, an addition, whatever, and then results would be written back to the cache. And one important thing here is that in modern CPUs or in recent years, we not only saw multi-core processing, so we have multiple CPUs, but inside the CPU, the execution unit has multiple different arithmetical logical units slash multiple vectorization units. So they can take a single instruction and apply it to multiple different inputs. And this is something we are going to come back later on because this allows us to gain a lot of efficiency. Looking at the cache, well, a cache is conducted of cache lines. This is the smallest unit the CPU can access. So if we want to access some data, we would always access the whole cache line. And each cache line belongs to a certain cache set. So usually CPUs cannot arbitrarily access any cache lines, but they are, due to the way we built these CPUs, they can only access specific cache lines for specific addresses in their address space. Okay, so to just give you some numbers to have a rough idea of what I'm talking about here, we can look at the energy cost of different instructions. So let's say a 32-bit integer addition costs roughly 0.1 picojoule for a 32 nanometer instruction set architecture, whereas the multiplication of a 32-bit integer would be 3.1 times. Would be 3.1 picojoule, which makes it 31 times more costly. Float multiplication is even a little bit more costly in the sense of energy. We see some behaviors in between. So for example, the multiplication of 8-bit integers is only 0.2 picojoules, so it's roughly twice as costly as doing an integer addition of a, well, 32-bit integer, which is 4 times larger basically. So the takeaway here is smaller data types are usually require less energy, and addition is cheaper than multiplication. Now, if you compare that to the cache, and this is where the real fun begins, we see that the access to the cache is roughly 5 to 50 picojoules, which makes it 50 to 500 times more costly. And accessing the main memory is even more costly, in the range of 3,200 to 6,400. Again, these are just very, very rough numbers, so don't quote me on those, but it gives a rough idea of what's important. So addition before multiplication, multiplication or computation before accessing any memory. Now last, so what devices do I think about when I say small devices? I think about stuff like an MSP430 from Texas Instruments, basically one core, 16 to 20 megahertz, depending on the version you got, with just a couple of kilobytes of RAM. And usually these are ultra low power devices which have 16 to 32-bit instructions and don't have any support for floating point or single input multiple data, so these vectorization I mentioned before. So the cool thing about those is that the power consumption is very, very low. That's why they often coined ultra low power devices. As a little bit more approachable in between thing, I would say it's an ARM11 or Cortex A53. So this ARM11 is basically Raspberry Pi 0, and the Cortex A53 is Raspberry Pi 3. And there you can see a drastic change. So it's in the range of 1 to 1.5 gigahertz with 512 megabytes of RAM. So that's already quite something. Both have floating point support and limited or full support for vectorization. And they require much more energy than the MSP430 versions, so they require much more energy than ultra low power devices, but they are still kind of okay. 1.5 watts for compared to the deep learning chip from Tesla requiring 57 watts we talked about earlier. That's already some gain in the resource efficiency. And just for reference, the i7 I mentioned before with 91 watts well, 4 cores, 4.5 gigahertz, in the range of 64 gigabytes of main memory usually, with all the floating point and SIMD support you need. So this is really the server hardware you go when you have big problems. So this is kind of the idea of what I'm thinking about when I talk about small devices. So how can we approach inference? And basically, the total energy is the amount of energy we consume in a given time period times the time we require for a computation. So that gives us 2 points of attack, basically. We can either use different hardware, which consumes less energy, and I've just shown you a couple of examples, or we can try to decrease the time we use this hardware, so the inference time gets smaller and smaller. And both are valid approaches to improve the overall inference speed and the energy, and thereby the energy we use. This is also kind of always related to the actual problem you have, because sometimes you have a problem which demands a certain kind of hardware. If you have an ultra low power problem where you don't have much energy, then you need to go for those ultra low power devices. If you're more freely in that, you can maybe say, oh, well, I can use the big Intel CPU because then the inference time is 20 times quicker than compared to when I use the Raspberry Pi. In that case, you would actually be more energy efficient because in total you would use less energy. So it always kind of depends on the problem. Okay, so in general, there are 4 different approaches how we approach fast inference. And the first one would be the most natural, is just to train a different model. So train a model which is more resource friendly. Instead of going for the big deep learning model, start with the linear regression and see what the result is. And if that's already sufficient, well, then just deploy that and go for it. I mean, we don't really need to use deep learning all the time. Another approach would be to take something which is already verified and trained, possibly by a data scientist, maybe from another department in the same firm, and change the model after training. So this way we would take something we know works quite well in terms of, let's say, accuracy, and then try to change it to make it more resource efficient. The third approach would be to use the hardware we have given differently. So with a careful implementation, for example, we could utilize SIMD way more, and this way gain some inference speed and reduce the total energy consumption. And fourth, we could of course design entirely new hardware. This is pretty much what Tesla did. This is what Google did with the tensor processing unit. If you have such a specialized use case, it could be worthwhile to just design a new chip for that. Now, designing a chip is a very, very different endeavor, and this is something. This summer school is about machine learning, so I'm going to focus on the first three parts here, and I'm going to give different examples for each of those approaches now. Okay, so let's start with the first idea: train a different model. And I'll start from the viewpoint of empirical risk minimization. This is basically a formula you have seen already. In this first part here, this is our standard machine learning approach, and then usually we like to add a regularization at the end of it. This is well researched and theoretically well grounded in machine learning, and this regularizer is used to combat overfitting usually. So lambda would be a trade-off, and R would be the actual regularizer. Now this framework is kind of interesting to us because it also enables us to incorporate resource efficiency in this regularizer. Or alternatively, we could incorporate that directly into the model class F. So we could say, okay, I will only look at decision trees and maybe linear regression. So this way I've guaranteed a very resource-constrained model class, which is well suited for a small device. But maybe then the loss will suffer because we will never get better than the linear regression or the decision trees in our model class. Alternatively, we can say, okay, well, we train everything from deep learning to ensembles to decision trees and linear regression, but try to guide the selection of those models using a regularizer, which, for example, punishes high memory consumption, large runtimes, stuff like that. Both approaches are valid, and it's depends on the specific viewpoint you have. So if you change the model class directly, then you have guaranteed performance in the end, because you can say, well, I never train a decision tree larger than depth 10, so my model will always be resource efficient. Whereas if you go for the regularization approach, you maybe have the trade-off of loss versus the regularization, so you might end up with a tree of depth 15, which offers significantly better loss or accuracy in this case. So this depends kind of on your viewpoint, but in the end, both are more or less equivalent. So this is kind of very theoretically speaking now, so let's give a concrete example. Usually, if you look at deep learning or neural networks, we have some architecture, let's say a convolutional neural network, and then the weights are real valued numbers. And one idea would be to say, okay, what happens if I constrain the weights to be either -1 or +1? And everything in between is just not possible. We just throw that away. We don't look at it anymore. And this is what we would call binarized neural networks. There are a couple of good works on that I cited here for you. And so the idea is we would train our usual deep learning model on a GPU and then deploy it on a small device to apply it there. And since binarized neural networks use weights which are either -1 or +1, we can store the weights and in-between operations in bools, so as Boolean and as integer variables. Whereas the more traditional neural network architectures require float all the time. So that means, roughly speaking, these models use 32 times less memory, which is already a great thing. As we have seen in the beginning, memory is very costly. So let's dive a little bit deeper into this. So a typical architecture would be something like this convolutional neural network, where we have some inputs, we apply convolution followed by a batch normalization layer, and then something which is called the hard-ton activation function or the step function, and possibly some max pooling. And this block would be repeated a couple of times and then followed by fully connected. So to further understand this, we can look at the input and output types of these layers. So let's assume that the inputs are either already Boolean, so -1 or +1, or integer. So for example, if you know the MNIST dataset well, then this is integers, for example. So the batch norm layer would apply transformation input times scaling plus some bias, and usually batch normalization has real valued weights, and this is something we will not change here because batch normalization is required for these types of networks to fully converge and to be trained in a meaningful way and to gain a good accuracy. So that means even though our X might be Boolean, S and B are real valued, so the output type would always be real valued. So this is a problem we have to take care of, and I'm going to discuss that on next slide. So hard-ton har, or the step function, basically doesn't have any parameters, and it would just look, okay, is the input above 0 or below 0, and depending on that, either output -1 or +1. And this is a Boolean again, in the terms of there are only two values. If we use max pooling, then of course the input type is preserved because we just compare stuff and then output something which is the same. Now if we use a convolutional layer, we would have to perform these two sums with the weights and the inputs. And so the question now would be, what is the output type if the weights are -1 +1 and the input, so this X would also be -1 and +1. And this is something I'm going to ask you to answer during the Q&A session. So I hope you have a rough idea of what's going on here. Similar, the fully connected layer is just a single sum, but it has a similar output type as convolutional layers. So again, the input X would be -1 or 1, and the weights are -1 or 1. And so what is the output type of this whole operation here? Okay, so what do we do about this? As I said, the batch normalization layer introduces float types, and this is required for an effective training, but for the application it's not really required. So what you could do is you can directly combine it with the activation function. So if we take the activation function and plug in the output of the batch normalization here, we see that we basically have a float here which consists of the bias divided by the scaling. And that means that's a value we can pre-compute after we train the model, but before we deploy it for application. Now, this still might be a floating point value, but keep in mind that we compare that against an integer or Boolean values. So this whole comparison can always be performed with integers. So that means that with this pre-computation, we can pretty much implement the activation function with a slight scaling and shifting combined with integer operations. So this remains in the realm of integer. So that's the cool thing about this. So how does the overall approach now look like? First, I always used weights -1 and +1 and Boolean values indistinguishably. However, that's not quite true, so we would have to map those to each other. So we map -1 to 0 and +1 to 1 to make it a proper bool. And now if we look at, for example, this multiplication here, this is exactly +1 if the two values have the same sign. So -1 times -1 would be +1, 1 times 1 would be +1, and 0 times 1 would be 0. And that basically is the XOR operation. Now we would sum over these 0 and 1 values, and that's what we would call a popcorn operation, and many computer architectures already ship that and come with this operation which we can just use. So pretty much what that means is that depending on the word size of the current architecture we're on, let's say this is a 64-bit computer architecture, we can process pretty much 64 bits in 2 clock cycles by combining the XOR and the popcorn operation. So this rather lengthy multiplication sum can be computed in only 2 clock cycles. So just to wrap this up, how does the usual training loop look like? So if you want to train those models, we would go for the standard stochastic gradient descent, meaning that we do the forward computation and then update the parameters of the network using the gradient descent step. Now the thing is that if we do this, if we compute the gradient with respect to the weights, which are either -1 or +1, we can't really compute the gradient because it doesn't exist most of the times. So what you would do is you would combine this with the deterministic binarization and the full precision stochastic gradient descent, meaning that you would compute the forward pass using the binarized weights, which are either -1 or +1, to get to the prediction of the network. But then for the backward step, you would keep the original values and the original gradients. And so what you would do pretty much is that you pretend that you would have binary weights to compute the output, and then using this output, you would compute the proper gradients in the proper backward step. This means that the training is usually slower because neither GPU nor implementations like TensorFlow or PyTorch are optimized for this setting. And so you would have to come up with your own function kernel basically to implement this a little bit quicker, but still in the end it would be slower than regular floating point operations because you would always have this mapping step in between. But that's not our goal here. We're not talking about fast training, but fast application. So what can you do with this? Just to give you a quick overview of what's possible. So we used this technique in one recent paper with a colleague, Lucas Fowler. I think you already heard the talk of him or watched it, or maybe you will after this. And so pretty much what we did is that we want to classify telescope data into gamma and proton particles. This is part of a sub-project here in the research center. And one of the takeaways we had is that the huge CNNs we would train would get an accuracies in a range of 91%, whereas depending on the way we would cut it after a couple of epochs, it's 94%, so that's a little bit better already. However, if you look at the binarized neural networks, you see that they are pretty much in the same range. So the regular floating point CNNs are in the range of 90, 91 to 94% accuracy, and the BNNs, so the binarized neural networks, are in the range of 88% to 93%, which is pretty good given that's 32 times less memory required to store these. So we try to put this on a small device, and I'm going to talk about that in more detail a little bit later, but just to give you an overview. We compared this against ONNX Runtime. This is a runtime engine by Microsoft, focusing on the fast application of deep learning methods or models. And as I just showed you, we had a small and a larger version, which are basically two different VGG architectures. The large one required roughly 21 milliseconds and 26 milliseconds, depending on if it's float or binary. This is kind of funky that ONNX Runtime actually gets slower when processing binary weights, but we assume that's due to the fact that we run those experiments on an Intel CPU, which is optimized towards floating point. And we're currently working on getting this stuff done on a small device, so in this case, the Raspberry Pi, for example. The small networks we composed are much, much quicker. This is roughly 1 millisecond to 2 milliseconds. And now we came up with our own implementation, which focused on the binarized neural networks. So in this case, the situation kind of reverses. Our float networks are not that optimized because our code was just not optimized to perform this really quickly. However, if you look at the binarized code, there you see quite the gain. So the large one is requires 11 milliseconds per event, which is roughly double as fast as before. Interestingly or weirdly, the small binarized neural networks is still slower than the small float network. And this is what I mentioned earlier. Sometimes it's important to see what kind of system do you have and what's the best model for the system. And in case of the Intel CPU, it might be better to go for floating point because the hardware is more optimized towards processing floating point. As a side effect of this approach we used here, we also generated FPGA code. So we were able to test this out on FPGA, and there we gained the most or the quickest solution for the small binarized neural networks, only requiring 0.6 milliseconds per event. However, if the network becomes too large and it doesn't fit entirely on the FPGA, the performance suffers quite a bit. So just to give you an idea. So to recap what we discussed in this first idea, well, we usually go for empirical risk minimization as deeply rooted in the theory of machine learning. And with respect to resources, we have two different views we can take on. We can come up with different function classes which are better suited for well, inference on a small device, or we can try to guide the search for a good model using regularization and incorporate costs into the regularizer directly. So that also means that if we have a small device and we want to come up with new solutions and we have a problem and need to come up with new solutions, that literature usually has starting points for us. Most of the time, even especially the older literature focuses on combating overfitting, but to some degree it has the same effect in reducing the model size or model complexity. So for example, if you look at decision trees, that would mean that we limit the height or the number of nodes in a tree, which again benefits the whole inference because now the tree is smaller. Same goes for ensemble learning in general, where we want to limit the number of base learners. Maybe just use 20 trees and not 128. Or use weaker base learners, so trees which have depth 1 or 2 and not depth 5. Similarly, we can find that in kernel methods where the regularization is already built into the whole idea and framework. In linear models, L0 regularization is a big topic. There's lots of papers on that, which usually means that we will throw away features we don't use. Again, reducing the complexity of computing the model. And then, of course, deep learning, there's a lot of stuff going on. I showed you just one example here, and if you search for that, there are a lot of different semi-automated techniques to come up with a good architecture which works well on a small embedded device. Okay, so now to our second idea, and the second idea is that we have a pre-trained, possibly validated model, and now we want to change this model so it runs faster on the embedded small device. And so I have a kind of quirky notation here. Again, we have a model class F, and now we are looking at a subset HF, which is derived from this one model small f we got. This is the one we got already trained, and now we try to select a model H from that. And just to make that a little bit clearer, formally the set HF would contain all the functions we would get if we use a maybe non-deterministic mapping function, which takes a model from class F and maps it to another model in class H. And then the whole approach would be, okay, let's train a model as usually. So again, the classic empirical risk minimization approach of achieving a small loss, maybe of a regularization. And this way we use to get to model F star. And now, given this model F star, we want to choose a simpler model H star, which pretty much does the same, but we are now selecting models from this reduced class HF star. And now this is again very theoretical, and let me give you a practical example so you know what I mean by this. So in deep learning, one of the easiest ideas, or let's say most direct ideas, to reduce the number of parameters and this way reduce the number of the memory consumption of a model is by reducing the number of bits you use to store certain weights. So instead of using 32-bit floating point operations, you can just go for 16-bit fixed point, and by that you already halve the number of bits you use basically. And you can do that to more extreme, so you reduce from 32 to 8-bit or maybe from 32 to 2-bit. So this example from 82 to 2-bit we have just seen with binary neural networks. The other examples can also be done as a post-processing, and usually the performance won't suffer that much, and you can just do that as post-processing. So you get a compression factor to 2 to 4 pretty much for free by going from a floating point to fixed point operations. But that also means that the predictions of your model slightly change, because we cannot guarantee that due to this change from floating to fixed point, we may have a change in the model output. That's important to keep in mind here. So how does fixed point look like? I hope at some point you got in touch with this. If not, well then this is it. So you basically decide that you have a decimal point at a fixed location, and you say, okay, I have, let's, for example, 2 digits before that decimal point and 4 digits after that. And so that means because this decimal point is on a fixed location, we have a fixed size. In this case, it would be 6. And that means we can use a fixed size data type, for example, char, to store this. And now, in order to go from fixed point to floating point, we would use this computation where the everything left of the decimal point would get multiplied by 2 to the power of the digit, so of 0 and 1 basically, and everything which is right of the decimal point gets the bits multiplied by 2 to minus the power of the digit, so -1, -2, and so on and so forth. And of course, if you want to implement that, we would never directly implement 2 to the power of something, but we would use shift operations. Similarly, you can go from floating point to fixed point, and I will leave that open for you, and we can discuss that later on if you figure out a way how to do that. Two things when we work with fixed point data types. For addition and subtraction, usually we don't require any changes. So that means if we have 2 fixed point numbers, they're pretty much depicted here as in their floating point version, and they both have the same scaling parameter, which means that the addition, we can just use a little bit of math here and see that this is basically the same. It's slightly different for the case that we multiply or divide something, because in that case we multiply x times to the power 2 to the power of n times x times 2 to the power of n, so we multiply 2 to the power of n twice. That means we have to correct after multiplication. And for division it's the same thing, only the other way around. So that's something we have to keep in mind, and this is a little bit quirky when using fixed point, because we can quickly run out of space and have an overflow or underflow depending on the range. Now, can we be a little bit more intelligent? This is usually the go-to simple idea. You go to an embedded systems person and they will usually say, well, just go for fixed point. And in a publication in 2015, Han and his colleagues figured out, well, the weights in the neural networks are usually Gaussian distributed. So you would have lots of weights very close to 0, and then only some weights which are bigger or smaller. And now if you look at the red dots, that's pretty much how we would sample these points using fixed point. And it might be more intelligent to use a finer grained solution, which would be the green points. So in red, this is fixed point quantization, and in green, that would be a more dynamic approach. And so how can we figure this dynamic approach out in a more coherent way? So there are two publications here which pretty much say that we take all the weights, cluster them, extract the centroids after clustering them, and use that to prune connections and possibly retrain the whole thing in the end. So what the whole approach would look like is that we train the network until it's fully converged, perform a clustering, for example, k-means, then using k equals to 10, for example, so we have 10 different weights, we would assign each weight based on the distance to its respective centroid and use those instead. And then we can retrain if we want to by ignoring all the other values we have in the network. Interestingly here, if we have a lot of zero entries, we can just prune them away. So that means that entire neurons can be pruned away if they're not connected anymore. The result in their experiments is that we have a compression size in the range of 20 without loss in accuracy. And now just to add on this, of course, if we have the distribution here on the left side, so a lot of weights which are near zero, and then we start to cluster them and we delete all the weights which are close to zero, then we will get a distribution looking like that on the right side, because we just deleted all the zero weights. And so another thing to exploit that is to use a Hoffman encoding to further reduce the size, because we now know for sure that there won't be any zero weights, because this is what we removed. And that gives you another additional 10 times compression size. So combining all those approaches, we are in the ratio of 35 to 50 compression-wise, so roughly 50 times smaller than before, which leads to a speed up in the range of 3 to 4, meaning we have 3 to 7 times less energy without any loss in accuracy, at least not actively measurable. But we train a lot of networks here. So we have pretty much this outer loop of training networks, which is super slow, and we need to do a lot of post-processing. Okay, just recap on that idea. So we take an already trained model and try to alter it a bit. This has the added side effect that we might change its output, so the accuracy might change. And the way we can do that, or the way we can view that, is as another empirical risk minimization problem, where we have this slightly different function class, in this case HF. The way we construct this class can be different. So the example I just showed you uses clustering, so it's not really deterministic how we do that. The first example before that, using fixed point quantization, that's deterministic, because the operation is deterministic. And so what we do now is that we train the model as usual, choose the simple model from the new model class, and then maybe repeat that on and on and on. And again, we have a lot of examples from other approaches in literature here. So for example, in decision trees, this is the go-to standard since basically the 80s. We train the full decision tree and then we start to prune it, which is pretty much the same argument here. You have a pre-trained model and then you change it a little bit. And of course, there's pessimistic error pruning, minimum error pruning, all that good stuff. In ensembles, this is something which came up in 2000 at some point. We take an already trained ensemble and try to remove base learners from this ensemble. For example, using semi-definite programming or Pareto pruning, stuff like that. Well, for linear models and kernel models, we can of course always remove unused features and specialty support vectors. This is pretty much what the SVM does per construction, but also weight clustering can be used here. And for deep learning, we just talked about that. We can prune the weights and connections, so we can do all this weight clustering stuff. But there are also more specialized versions out there. For example, we have convolutions which have a fixed special structure and which are never changed, for example. Okay, so far we talked about models a lot. But what about implementations? And there is one publication actually posed this question, okay, are we comparing algorithms or are we comparing the implementation of algorithms if we look at runtimes and the performance? And so for us here, the implementation takes a very special place because the implementation must respect any specifics from the model. For example, if we take a binarized neural network and we know the weights are -1 or +1, it doesn't really give us much if we store them in floats. So we have to make sure that our implementation knows that and uses that knowledge in some way. On the other hand, the implementation must also respect any specifics of the hardware. So, for example, if we have vectorization operations we would like to use, then we need to make sure maybe that the base data types are at least char or maybe integers. So usually vectorization doesn't work for Boolean values because this would already be, so the smallest data type is char or integer depending on the architecture you're at. So your implementation must also respect that. That means if you have a binary or a binarized neural network and you want to execute it with vectorization, you have to make sure how to map that properly. Because on the one hand you have -1 and +1 or 0 and 1 as a Boolean. On the other hand you want to use vectorization which requires, let's say, char. So there is some blow up going to happen in order to make this work. The question is, in the end, is it worth it? Should we do that? And so this is what I want to talk about in this part of the talk, a little bit more about implementations and how we shift towards decision trees, because they're fairly easy to understand, but still kind of interesting to use. And so in any modern programming language, you will at least have two ways to implement a decision tree. The first one, this is what I would call the textbook way to do it, is to come up with a struct or some class or something which stores all the information from each individual node. So what's the left child, what's the right child, what's the feature value, what threshold are we comparing against, stuff like that. You would put that in one single array. And then you would just traverse the tree using a simple while loop. So you check, okay, you started with a root node per construction. This is, let's say, at the 0th location in this array. And you check, okay, is that a leaf node? Okay, it's not a leaf node, we are just at the root node. Then let's extract the corresponding feature index and access the corresponding feature from the feature vector we just got and compare that to the corresponding threshold, or split value in this case. And then we would just map I to either the left or the right child. And we would repeat that over and over and over again until we would reach a leaf node. And then in the end, we would just return the prediction of the leaf node. And that's the fairly easy standard way to do that. Another way, arguably even easier, would be to unroll a tree into its if-else structure. So because we don't want to change the model after we use it, after we train it, we can just do this and just use it the way it is. So for example, we compare the first feature against some pre-computed threshold. If that's not true, we compare it against another feature, another threshold, and then return true or false depending on the label. So this is even easier given that the tree is already pre-computed and we just unroll it basically in the structure. And so these are two different approaches. Interestingly, there is a third one which we can use with the way modern CPUs are working. But before we do that, I would just ask you, okay, what's the caching behavior of those two different implementations? So keep in mind we have a data cache and an instruction cache. The data cache caches, well, data, and the instruction caches instructions. And usually instruction cache is a little bit smaller than the data cache. So with the Intel CPU, for example, we have an instruction cache in the range of 265 to a couple of megabytes, and instruction caches are in the range of 265 kilobytes, not more. And just think about it: what would those two implementations, how would they behave with respect to caching? So now let's talk about a third way how to implement decision trees. And so before we do that, let's look at this tree I presented here. So this tree has a couple of nodes, the root node 0, and then 1, and 2, and 3, and so on and so forth. And recall that tree traversal is that we in the root node, we would check a feature value of our current feature vector, so let's say xf, and we would compare that against the pre-computed threshold t. And depending on this operation, we would either go to the left or to the right subtree. Now, one way to view that or to implement that is to assign each of the leaf nodes a single bit, which indicates if this is still active or inactive. And at the end of the day, or at the end of the traversion, we want to have everything is inactive except of one leaf node, and this is the one we would use in the end. And so let's, for example, look at this one here. If the root node evaluates to true and we go to the right part of the tree, those three leaf nodes cannot be reached anymore. So that means that if we take a bit vector where the first entry would be active, inactive of node 7, the second would be inactive, active node 8, and so on and so forth, we would have to invalidate the first three. So the bit mask here contains 3 zeros, and if we would perform a logical AND operation, we would basically zero out those 3 here and leave those 4 in active mode. And that's the basic idea. So as soon as we've evaluated all the false nodes, so we invalidate all the different nodes which are false, then we know that there is only one left, which is 1. So let me give you an example. I think that's the easiest way to explain that. Assume that 0 and 1 evaluate to true, and the rest is evaluated to false. So true means we go to the left, 1 means we go to the left, false means we go to the right. So 8 would be the one we are looking for. And now let's do that in terms of bit operations. We would start with a 1-bit vector, so every leaf node would be active. Now we said we need to evaluate all the false nodes, and 3 is a false node, so we would need to use this bit mask for an AND operation. Also this one, and this one. So we have 1, 2, 3, 4 different bit masks we need to perform an AND with. And now doing that would basically mean, okay, the first one is 0, the second and the third one is fine, the next 2 need to be 0, and then there is 1 again which needs to be 0, resulting in a bit string of 0, 1, 1, 0, 0, 1. And now we look at the leftmost of those bits. So 0, okay, 7 is inactive, that's 0. 1, oh, that's the first one we got with the 1, so this is the one which is active, so this is 8. So the important part is here that we need to process all the false nodes, so all evaluations in the entire tree which are evaluated to false need to be processed. And then we need to extract the leftmost bit, which is still 1. And Lucchese and colleagues give a proof for that, why it's the leftmost one. It's a rather simple proof, to be honest. You just have to think about the argument once, but there's not a lot of math involved. So I will leave you with a second example we can discuss later on. And let's continue. So the thing is, if we do that, we need to evaluate all nodes potentially. So because we don't know prior if there is a false node or not. So worst case scenario, we need to evaluate all decisions in a decision tree, which is definitely more than what we would have used to if we just process the tree in order. So their idea is to use this across the entire ensemble, and that's what the quickscorer algorithm pretty much does. So we take the entire ensemble, deconstruct it into its individual decisions in each decision tree. So there are a lot of different decisions involved, but some decisions can be reused across the whole forest or across the whole ensemble. So what we would do is we take all the decisions, so which are pairs of feature and the threshold computed, sort them for each feature accordingly to their splits, and then we would just loop over all the features and check all the splits. And as soon as we find one true comparison, we know that all future ones will be true as well because of the sorting. And so the sorting is a pre-processing. This is nothing we need to do on the fly. This is something we can do once we train the model. And that means we will only need to evaluate all the false nodes, and we will only evaluate one true node. and exit as early as possible. On top of that, because we are dealing with bit masks here, we can come up with a very clever implementation which only utilizes single arrays and minimizes indirect memory accesses. For that, I would refer to the paper. What's pretty cool about this algorithm is it skips as many comparisons as possible. So it will only compare those values which you would actually need to compare. Because as soon as you find one true comparison, you will never compare any other of the comparison in the one tree, and in the entire forest even. On top of that, because it's so structured in a way of the comparisons, it is very easy on branch prediction and caching, because you would have one pipeline, so one miss basically. This is when you go from evaluating false nodes to true nodes, but this only happens once per feature throughout the entire forest. So this is very easy on the branch prediction and caching. The problem though is we have a very bad worst case, because in the worst case we would need to evaluate all the different decisions in the entire forest. So if we have exponentially many decisions per tree times the number of trees we have in the forest, we get away with a lot of comparisons, and sometimes it might be better to just compare it regularly and not use the quick-scorer algorithm. This entirely depends on the way your data and your forest looks like. Second, an efficient implementation requires that we use the word size or maybe vectorization. In that case, we are always limited to the word size of our machine basically. So with a normal Intel CPU, it's 64 bits, so that means depth 6 is the way to go, because well, we need a value to hold all those bit values for all the different leaf nodes. And if we have depth 6, then we can have a total of 64 leaf nodes, which is one variable basically. But if you think back and go back to the example of the MSP430, which only has 16-bit words, for example, then we would have way shallower trees basically, and not so many leaf nodes, because we could only get away with 16 leaf nodes. There are a couple of extensions to this algorithm. So first of all, the baseline quick-scorer algorithm is already 2 to 6.5 times quicker than the baseline. The baseline is the textbook tree or native tree, I called that. I showed you in the beginning, which only has one while loop and an array loops over. Then they came up with the vectorized version, which basically scores multiple examples at a time. This already is 1.5 to 3 times faster according to their experiments. And then rather recently, the rapid scorer algorithm came up, which kind of tries to get away from this hard limit of the tree depths by using some funky way to do the bitmask encoding and to do some compression on the fly, while keeping the vectorization capabilities. And this is roughly 1.3 to 5 times faster than the quick-scorer algorithm. And so the story kind of builds up that this is a very quick algorithm. Unfortunately, I cannot show you any experiments I have done with this algorithm, because it is currently under a patent pending. So I talked to the authors and they kindly gave me their source code and I can use that, but I'm not sure if I'm allowed to publish any results using that. And at some point, maybe somebody should come up with their own implementation. Okay, so this is one way to do it. Now I want to discuss a different way, and this is something we developed here at TU Dortmund University together with colleagues from the embedded systems group. And our basic idea was, well, if we traverse a tree, there are probably parts of the tree which are used more often than other parts. And if we think about caching, it's a good idea to keep those parts which are used most often in the cache. So, for example, if you look at this tree again, we can just take the training data we have and classify it with the tree. And maybe it turns out that this path from 0 to 2 is taken 70% of the time, whereas the path from 0 to 1 is only taken 30% of the time. That means that it might be a good idea to keep the node 2 in the cache, but not node 1. And with this way, we can assign each pass a given probability. and what's the probability to perform a given cache. And then we can also leverage that and come up with the expected path length, so which is the expected number of comparisons we need to perform per tree in our forest. So to give you a quick example here, let's say we would go down this left road from 0 to 1 to 3. That basically is 0.3 times 0.4 times 0.25, which equals to a total probability of 0.03. So it's rather unlikely that we will ever use this part, given that the training data distribution matches the one we have in testing. Now, if we look at the rightmost part, so path, so 0 to 6, we come up with different probabilities, which is 0.7 times 0.8 times 0.85, which totals to something close to 0.5, which means that this rightmost part will be roughly used 50% of the time. So if we just keep this part in the cache, we will have 50% of cache hits, which is already quite good. And so we were thinking about how can we utilize that, and so the next idea is to just compute that part of the tree, which we later called the computational kernel of the tree, and make it so that it fits in the cache. And the solution we came up with, we called it tree framing in the end, because it kind of shapes the tree in a way that it fits in the cache nicely. So we give a computational budget. This is pretty much what can fit into the cache for the given system we have. And then we try to maximize the probability that something is used which we place in the cache while respecting the budget we have. And so this number here, this is kind of important to talk about. So as of I, this is the size of node I in terms of the assembly. So this is what actually needs to be put into the cache in the end after we compile the application. And so this is very difficult to come up with, because if we take the source code, it's difficult to project or get an idea of how much memory it actually uses. So you need to compile it, look at a disassembly for different versions of the implementation target system, as well as optimizations you would enable, let's say with Clang or GCC, and come up with a coherent number here. So this is something the embedded system guys, for example, are experts in, and they have helped us here a lot to figure this one out. The computations of the probabilities are straightforward. You can just do that with the training data you got, and then we just greedily optimize that. And the cool thing about that is, so this budget, this can be chosen in accordance to the CPU model you have. And this might be different for the Intel i7 versus an Intel i5 versus an ARM in Raspberry Pi versus the ARM in your smartphone. And so we can really fine-tune the implementation for each specific model, CPU model in this case. So I want to show you some numbers here. Of course, we compared this one against the if-else and the native tree I've shown you in the beginning, and we can do this kind of optimization for both types. So we can do that for the data as well as for the instruction cache. And there are a couple of other smaller optimizations we came up with in this paper to just compare the different types of optimizations we have. So let's look at this here. On the x-axis, we see the tree depths. So 20 would be trees of depth 20 and 5 depth 5. On the y-axis, we see the speed up compared to the native implementation. So this is our baseline. And so 5 would mean we are 5 times faster than the baseline implementation. And so what we can see is in the beginning, so for very, very small trees, we get a tremendous speed up already, which interestingly is negated for the native tree in the end. So if we use deeper trees, the optimizations don't really matter. But the if-else trees combined with the optimizations, they kind of fold up. And only in the range of 20-ish, we see that they kind of are on the same level. But as a bottom line, we can say, okay, this is something in the range of speed up to 2 to 4 or 5-ish, depending on your data set, which is pretty good. So I would ask you to come up with your own takeaway. I just gave you some interpretation of the data. But so what is your takeaway? What would you recommend if somebody says, okay, I have an ARM so Raspberry Pi 3, and have this type of ensemble. So what would you tell them? What would you use for implementation? Okay, so let's also just recap that really quickly. So implementation has a very unique place in FastInference. It must respect the model from a machine learning point of view as well as the hardware. So again, the literature offers some starting points here. For example, we just discussed that we have if-else trees, which is a rather old idea. We have techniques like tree framing. We have stuff like the quickscorer algorithm I just talked about. For linear and kernel models, there is a lot of stuff going on in the range of SIMD and GPU acceleration. But there's also something like hardware-friendly kernels, which are fixed-point kernels pretty much. And this gives rise to the fixed-point SVM, which still retain a lot of theoretical performance and is quick at the same time. Looking at deep learning, we can talk about fast Fourier transformations, which are sometimes used, especially in the range of image processing. Vinograd convolutions, which are more heavy on summations, which I told you in the beginning is not that energy heavy. So we can trade some multiplications with summations if that's good. So again, there's a lot of stuff going on in literature. And this is not the last part of the talk. I want to talk about all the stuff happening in literature and research at the moment. We need to talk about tooling for a second. Before we do that though, you can try to come up with pros and cons for the 3 different approaches I just mentioned. So we talked about training a new model, and there are some obvious pros to that, but also some cons. Similarly, the second idea was to change the pre-trained model, and the third one we just talked about was to come up with an optimized implementation. And I would just ask you to come up with your own ideas, what's good in what situation and what's bad, so what's the pros and cons. And I would like to discuss that later on in the Q&A session. So, tooling support. If we look at deep learning, there is, well, a shit ton. We have ONNX runtime. I mentioned that really quickly. This is probably one of the bigger players and the most complete one yet. Apache has something called TVM. I never used that. There is Glow, TensorFlow Lite, and TensorFlow something processing. I'm not quite sure what's the difference between those two. I think they are 2 independent projects which are kind of doing the same. Of course, NVIDIA ngraph and OpenVINO. Then we have TensorRT, which is also from NVIDIA, which is kind of weird that they offer multiple versions. We have Fin, which is from Xilinx, so it's more targeted toward FPGAs, and many more. So if you start to Google that, there's a lot of stuff going on, and you can pretty much lose a day or 2 or 3 to just Google those frameworks. So what I've found though, and this is just what I want to share, many of those are not at a state that you can just use them. I would say ONNX runtime is kind of an exception, and TensorFlow Lite as well as TensorRT and ngraph, because there are big companies behind that doing a lot of work in this direction. But if you take your weird deep learning architecture you just came up in the last couple of weeks and want to deploy that to a small device, it's kind of difficult to come up with an optimized implementation here. Again, these tools are more targeted towards the average use case, so like convolution, maybe an LSTM, BERT models, for example, are also highly optimized in these frameworks. So there is something, but it's not like you can just use it and it's working. You have to do some work yourself. If you look at tree ensembles, the situation gets a little bit different. Pretty much quickscorer I mentioned already. If you ask nicely, the authors will usually give you the source code, but I'm not sure if you're allowed to use that. Then there's something called TreeLite. This is a model compiler which pretty much produces these if-else trees I mentioned before, and this works fairly well. They have C++ or C code, I think C code it is, as a backend, so if you have an embedded device using C code, you can just use that. Apart from that, there is not much. So I know that Vekar, for example, also supports the exportation in as C code, I think, but that's pretty much it. If you look at all the other models, there is this weird in-between state. So technically, the ONNX format, so the Open Neural Network Exchange format, allows you to also implement the SVMs or linear models or even decision trees inside the specification. So technically, ONNX runtime should be able to come up with the well, good implementation for those because it's much more general. But I tried to use that for decision trees, and I found that ONNX is vastly underspecified. There is no agreed upon way to, let's say, implement a decision tree. And so ONNX runtime will usually fail because some weird clunkiness doesn't really add up. So the only two frameworks I know about is CoreML from Apple, which I don't really know how good that works because I think it only works together with the tools from Apple. So you cannot really export, let's say, a gradient boosted model from XGBoost, but you have to come up with your own solution inside the Apple ecosystem. And then there is something called Hierachy, which is a weird thing, kind of doing the same as TensorFlow XLA, I think, but again different, but also Google, I'm not quite sure. But they try to come up with pretty much something like the Java virtual machine for machine learning. And there's a lot of stuff going on in this repo, but I have not figured it out fully, to be honest. But they claim that they can do more. So what I want to say now, or what my focus here is, these are all good and nice, and I would definitely recommend using them if you have a problem which suits this. But if you have an embedded system, and I mean like a real embedded system, bare metal, small microprocessor, where there's no runtime environment, no Linux running, nothing at all, you're pretty much effed with these kinds of tools. So ONNX runtime has C backends and C bindings, but it uses Python and it requires a whole runtime engine. Quickscorer and Treelight would be okay. You could maybe figure out a way to cross-compile those, especially Treelight should be possible. If you look at NVIDIA ngraph, for example, this is their whole NVIDIA ecosystem, and you need to, well, it takes a couple of days to even compile that for Raspberry Pi, which is already weird way to do, a weird thing to do. So if you now want to put that onto, let's say, Raspberry Pi Zero bare metal, you need to cross-compile it, and hopefully some way it works out. You can try that, but I'm not sure if it works. And so this is where we kind of chipped in. And because I'm lazy, my idea was, isn't there a way to generate the optimized code for every hardware and model directly on the fly? So now I know all these techniques, I've read the literature. Is there a way to just generate on a model and so hardware and machine learning model specific basis optimized code? And this is what we are currently developing here at TU Dortmund University. We call it FastInference, and the basic idea is that you take a trained model. In case of, let's say, decision trees, it's a JSON file. In case of deep learning, it would be an ONNX file. Read that file. Currently, we support linear models, ensembles, decision trees, and neural networks. Put that into some internal data structures on which we can perform optimizations if we want to. So, for example, we could start with weight clustering, or we could perform tree framing. I just explained that to you. Then we would choose the target architecture. Regular Intel, maybe some weird ARM architecture, or even an FPGA. And now the tool would figure out, okay, we are on an ARM architecture, so I need to do a multiplication. There is this weird multiplication on ARM architecture, which I can reuse now for all the multiplications in the model. And combine that with templates we have pre-programmed and shipping with it. So for example, if we have a regular neural network with floating point convolutions, we have a small code snippet for that, which contains a lot of placeholders, and with these placeholders are just replaced by the architecture-specific informations. Similarly, for binary convolutions, we also have this. And for example, if we want to use the popcorn operation because it's available on the target architecture, we just replace it accordingly. Or if it's not available, we provide our own implementation for that. And so what happens if we do it this way, we read a model and we pretty much output a very, very large and long C file, where the whole model and the whole application of the model, including all its weights, is just piped into and can then be compiled. This has two very big advantages. The first one is whenever somebody comes up with a new model, we can simply add some templates for that. So let's say we want to support residual networks, so ResNets, then we need to come up with a ResNet layer basically and give the appropriate implementation for that. Similarly, if we want to have a backend which is specifically targeted for FPGAs because we want to do that in VHDL or Verilog, we can just provide templates here as well and just provide those code snippets. But the rest of the tools, so everything which happens basically before that, so in this part, remains the same. You can just use that and add some templates here. Similarly, if somebody figures out a way to optimize a model differently, so a different form of weight clustering or a different way of tree framing, you could just implement the optimizations here. Because everything which happens afterwards is only based on the optimized models. So this way, the whole method is very, very flexible. And we can just add new stuff, try out some stuff, as well as have this bare metal approach where we don't need any runtime environment. On the negative side though, of course, this is a two-step process. So we need to perform code generation and compilation. This is a little bit more clunky. It's not directly pip install something and then use it. It's always a two-step process. And some optimizations cannot really be performed in these templates. So we need to figure out a way how to make these kinds of optimizations work. So the status currently, just to give you a heads up, I would have loved to put in a link here in the slides, but we're at this time of recording this not there yet, but maybe during the Q&A session. So we can pretty much read linear models, decision trees on ensembles trained by scikit-learn, and we can generate the implementations for that. And due to some version mismatches, not all of the optimizations we had previously, so not all the optimizations with tree framing, for example, are yet in this framework, but we are currently trying to get it in this. Similarly, so if you have a neural network model, let's say trained with PyTorch, you can export that as an ONNX model. And convolutional neural networks as well as binarized neural networks do work. This is what I showed you in the beginning with the runtimes. And a student is currently working on implementing ResNets in this kind of framework. So what did we talk about in this talk? So first of all, I gave you two different examples. The first one was Tesla's autopilot, and the second one was Bing.com, and both showed that the energy requirements are rather huge if you look at this scale of a machine learning application. So we need to think about how to apply models efficiently in order to save energy. Then we discussed 4 different ideas. The first one would be to train models which are more aware or more better suited for resource-constraint devices. And we discussed the example of binarized neural networks here. Second idea would be to change the model after training. So we take this pre-trained, already valid and verified model and alter it a bit so it runs better on the small device. Here we discussed weight clustering and neural networks. Third idea, we discussed the special place of implementation for fast inference, and I gave you 2 examples. The first one was Quickscorer, the other one was tree framing. Quickscorer uses bit masks to evaluate the entire forest, whereas tree framing focuses on putting specific paths of a decision tree into the cache. Fourth idea would be to just use different hardware, and so if you're in the place of choosing the hardware in the first place, this is something you should definitely consider. If you're doing research in this area, this is also something you should consider to come up with machine learning accelerators, basically. Apart from that, it is not a main focus in this talk. And so I showed you a couple of specialized tools, and I would challenge you to just Google those and look it up and try to use those and see if it fits your use case. And if it doesn't fit your use case, or if you're just interested in this whole thing, we have our FastInference code generator coming up, and we're still looking for applications, and we're still trying to enhance the whole implementation. So this is what's coming. With this, I'm finishing my talk, and I hope you had some fun, and I hope I can see you during the Q&A session. Bye.